Welcome to NPTEL lecture series, a basic course on electric and magnetic circuits. We are in module 2 on AC circuits, and this lecture is on different AC circuit problems, complex problems, typical situations. So, let us go one by one on these problems. So, the first problem is having a circuit like this, where we have 10 and 30 ohm impedances in series, 12 and 20 ohm also in series, and they are connected in parallel, branch 1 and branch 2, with a series impedance of Jx, and then these are connected to a voltage source, 100 volt source, having omega equals to 314 radian per second. The question is, find the value of the reactance X in the circuit for which the current through X becomes maximum and the corresponding current. So, the current becomes maximum through X, or that from the source, voltage source, 100 volt voltage source, and the value of the reactance we have to find out, and what is the corresponding current value. So, this is a situation which we have already discussed in our earlier lectures, having series parallel combination of the impedances. So, here in this case, when the corresponding Z equivalent, the total impedance of the circuit seen from the source becomes resistive, only resistive, it means that all reactances cancel out, then we have that is the minimum impedance case, and the corresponding current becomes maximum. So, all the data are given for this except the Jx value. So, the corresponding Jx value will be depending upon the reactance value of the series parallel combination right of the Jx, and then from that one we will fix the corresponding Jx, so that it nullifies all the reactance of the other portion, and the corresponding impedance seen from the source this side, that becomes Z equivalent or Z total, that becomes resistive, and the corresponding current becomes maximum from the source at that time. That means that corresponding current becomes maximum from Jx. So, we will go by that. Then for the circuit, the total impedance, that becomes equals to Z total equals to Jx 10, 30 in parallel with 12 plus 20. So, this gives us the this part series parallel combination, these two part, that becomes equals to 17.596 J 2.1 ohm, and that is added with Jx in series. So, current through X, that becomes I equals to 100 with the corresponding Z total seen from the source side, and the Z total is minimum when it becomes a resistive circuit. So, that Z total should be, this should be a resistive circuit. So, that means that the Jx should nullify the corresponding this part. So, then that means that the J of X should be equals to minus J 2.1 ohm. So, therefore, X becomes equals to 2.1 ohm, a capacitive reactance. So, this reactance will be a capacitive reactance in this perspective, and this is clear also, because the corresponding reactance, this is a resistance, the reactance here is inductive, the reactance here is also inductive. So, the parallel, this part will give us an equivalent reactive inductive reactance, that is what we talk about this part, and therefore, this has to be capacitive to nullify the reactance, and that is the outcome. The X happens to be minus 2.1 ohm, a capacitive reactance. Now, at this situation, the corresponding Z total becomes equals to that only resistance part 17.596. So, therefore, the corresponding current becomes equals to 100 volt upon 17.596, and that equals to 5.68 ampere. So, this is the corresponding current through the J x part when the current is maximum and x becomes equals to when x becomes equals to minus 2.1. Now, we will go to the second problem. Question is determine V 0 time domain V 0 here across the 1 ohm or the corresponding current source or across here in the circuit. So, in this circuit we have time domain expression for the current source and also time domain expression for the voltage source, but note both these sources are having a omega equals to 4 radian per second. So, both are having same frequency. So, this is the best fit for a phasor while handling the corresponding circuit with phasors. So, as already we have discussed earlier also. So, we will use the corresponding phasor concept for this, and because the corresponding omega is 4 and the corresponding reactance value for the capacitor we can find out x c equals to 1 by omega c, c is 1 by 12 farad, omega is 4 radian per second, and for the 2 Henry also omega L we can find out the corresponding reactances. And these two sources, if we assume this to be reference, so this will be with the phasor transformation we can go by this 2 by root 2, that is RMS value, peak is 2 with an angle of 0 degree for 0 degree ampere, then this one will be lagging by this one with 90 degree. So, this becomes equals to 16 divided by root 2, peak is 16, RMS is 16 by root 2, and this will be with an angle of minus 90 degree volt. So, with this and then the corresponding resistance and the reactance X c minus J X c rather, and this is plus J X L, and this is 6 ohm and this is 1 ohm, then the circuit is an AC circuit with phasor value of voltage and current sources. So, now we can analyze with the circuit with a nodal method, because we have only one node here. So, this node and this node voltage is nothing but the phasor of this V 0 that is V 0. So, that is directly we can find out the corresponding V 0. So, in the nodal method we see here, so we have this branch V 0 minus V 0 upon this impedance, and this is the current coming entering to this node, and V 0 upon 1 ohm is nothing but current outgoing here, V 0 upon V 0 minus this 16 by root 2 minus 90 upon 4 minus J X c will be nothing but the current outgoing, 1, 2, 3, 4 currents will be getting. So, now if we write the corresponding nodal equation, we can solve the corresponding V 0, and once you got the corresponding V 0 phasor, then from the V 0 phasor we can write the corresponding time domain expression for V 0. So, that way you can proceed to find the solution for this case. So, as I said, this omega is 4 radian per second, 2 cos 40 in phasor it comes out to be 2 by root 2 0 degree. So, root 2 0 degree ampere, and 14 sin 40 this part voltage phasor voltage source happens to be minus 90 degree. So, that becomes equals to minus J 8 root 2 volt, and the reactance for 2 Henry is J 8 with L equals to 2 and omega is 4, and reactance of this 1 by 12 farad capacitor happens to be minus J 3 ohm. So, the circuit becomes this one, original circuit becomes it looks like this with a voltage source this and the current source root 2 with an angle of 0 degree ampere, and the corresponding impedances, reactances, resistances are provided like this. So, now the circuit is available, we need to solve this. So, let us we define this as node A, then at node A we will write the nodal equation. So, we have 4 branches 1, 2, 3, 4 currents. So, if you see here for this part, so the current becomes equals to, and note that this A has a voltage of this voltage is same as A voltage, this voltage is same as the VA voltage. So, it degenerates at V 0. So, this becomes equals to, we see here that this voltage minus V 0 is incoming and this is root 2 is incoming. So, I can say that this voltage minus V 0 is incoming and root 2 is incoming. So, this is the part incoming current should be equals to outgoing current. So, V 0 divided by V 0 by 1 this is the outgoing current, and V 0 by 6 plus J 8. So, incoming current this part, outgoing current this part. So, then we equate this one, and from there we can find out the corresponding V 0 phasor, that happens to be 2.711 minus 35.02 degree voltage. So, we get from the nodal voltage approach, from the phasor circuit, phasor based circuit, we got the voltage to be 2.711. So, this voltage we got that. Now, then this voltage is same as this voltage, voltage across 1 ohm resistance. So, therefore, the V 0 t expression, because we took the corresponding 0 degree expression for the cos term. So, therefore, this becomes the corresponding expression becomes 2.711 into root 2 cos 40 minus 35.02 degree, and this becomes equals to 3.835 cos 40 minus 35.02 degree volt. So, this way we can solve the circuit time domain expression we got from the phasor analysis. The next problem is on a circuit like this. So, we have a current source and we have a voltage source, and both are having omega equals to 1 radian per second, same frequency. Current source is having 3 with an angle of minus 60, and voltage is having 4 with a 0 degree volt. So, now the question is that in this circuit we have a resistance, inductance, capacitance, resistance, and we have two nodes V 1 and V 2. Using nodal method, find V 1 and V 2 for the circuit shown. Find also the complex power delivered by each source, Determine the value of the reactance to be connected across the voltage source, so that no reactive power is supplied or received by this source. So, we will connect a reactance here, suppose and I put reactance like this. So, J of x. So, what will be the value of the reactance here, so that the corresponding source does not contribute any reactive power, neither consume nor deliver. So, that is the condition we are imposing. So, before coming to that, we will first solve the corresponding nodal method here, and we will at each node we will write the corresponding equation for the solution, and then from there we will find the corresponding V 1 and V 2, and afterwards we will find the corresponding complex power handled by the corresponding each source. So, now for the complex power we know this is V I conjugate. So, for this source this will be V is 4 with an angle of 0 degree. So, once you know the corresponding current here, then you can find the corresponding V I conjugate for this source. In this case, the corresponding current will be nothing but this voltage minus V 1 upon 1 ohm is nothing but the corresponding current. So, once you know the V 1 phasor, we can find the corresponding current from the voltage source, and then we can find the corresponding complex power S of the voltage source. For the current source, now we need to, once we know the V 2 and V 1 and V 2, so the arrow mark points to this V 1, V 2. So, what we will find that voltage across the current source is required. So, that becomes equals to V 2 minus V 1, that is nothing but the voltage across the corresponding current source. I designate it as, let us say, V I, and once you know the V I phasor into the corresponding current 3 with an angle of minus 60 degree, then that becomes the corresponding complex power for the current source. So, that way you can calculate the complex power for voltage and current source. And the next part is about the to find the reactance when the corresponding reactive power supplied by the voltage source happens to be 0. Now, at this condition, if you see the circuit, this is an ideal voltage source. So, this term right hand of this J x also happens to be same. So, even if you connect the corresponding J x, the right side of this circuit will not find any difference, because the voltage of this will be maintained 4 with an angle of 0 degree maintained to the right of this J x also. So, this J x here what will happen locally with the corresponding voltage source will adjust with the reactance such a situation that the corresponding reactive power contributed by whatever contribution it comes from the voltage source happens to be 0. So, we know that we have already found out the corresponding S equals to V I conjugate, which you can write in the form of P plus j Q also. So, this Q is nothing but the reactive power associated with the voltage source. This Q must be 0. So, to make the corresponding Q 0, we need to adjust the corresponding J x. How to adjust the J x? We will narrate that one, because this is load and this is the source. So, we know that in a generic circuit, if this is a source, let us say voltage source, and this is a load, let us say an impedance, this is an impedance. So, now let us say this impedance consumes a power of P plus j Q complex power. So, this P plus K Q must be supplied by this P. So, this also P plus j Q. So, here P, here P, here Q, here Q. This is generation side, this is generation side, this is load side. So, in a circuit smaller, bigger, whatever, then the corresponding generation and the load, the corresponding P of the generation, total P of the whole complete generating units and total P of the load, they must be same. The total Q and this total Q of the load side must be also same. With that concept and approach, we will find the value of the corresponding J x. We have two sources in this case, and what are the associated Q? We have different loads here, and what are the corresponding associated Q, and we will balance these two and find the corresponding Q required by the J x part, and from there you can find the value of x. So, let us go by the one solution. So, first part is to find the corresponding solution for V 1 and V 2 by nodal method. So, here we have two reactances for 2 Henry and 1 farad, omega is 1. So, the XL, L part is having j omega L, that gives us j 2 ohm, and XC part with omega equals to 1 gives us minus j 1 ohm. So, now at A, node A and node B, you can write the corresponding KCL. So, here three branches are there, 3 currents associated. At B also there are 3 currents associated for KCL. So, at node A, we have V 1 minus 4 upon 1, V 1 upon 2 j reactance, and the corresponding outgoing current is this. So, all outgoing currents, sum of all outgoing currents equals to 0, 3 are there. So, that leads to the corresponding V 1 value happens to be 3.225 with an angle of 72.667 degree volt. So, what we say that we got the corresponding value of the V 1 at node A from this first nodal equation. Similarly, at node B, second node equations, we have V 2 here. So, we say V 2 by 2 this part, this current, and then V 2 by minus j this current, and then the incoming current is this one. These are outgoing current equals to incoming current, 3 with an angle of minus 60 degree, 3 with an angle of minus 60 degree. So, this gives us the corresponding V 2 to be equals to 2.683 with an angle of minus 123.435 volt. So, we got the corresponding V 1 and V 2 in magnitude terms. V 1 is having 3.225 volt and V 2 having 2.6833 volt. Now, we leave this V 1 and V 2 value to find the corresponding complex power as in the next part of the question. The complex part associated with the voltage source and the corresponding current source. The current source I, the current source I, the current through voltage source 4 volt voltage source I 1, let us say this is I 1. So, this I 1 equals to 4 minus V 1 upon the resistance 1 ohm. So, this becomes equals to 4.326 with an angle of minus 45.37 degree ampere. So, we got the current from this one. So, therefore, from the positive terminal the current is being delivered. So, we can find the corresponding complex power delivered by this 4 volt source equals to the voltage 4 into 4 with an angle of 0 degree I 1 conjugate. So, this gives us the corresponding I 1 conjugate means minus 45 will become plus 45, and that gives us the corresponding P plus j Q form 12 plus 157 kilowatt plus J 12.314 var, sorry 12.157 watt plus 12.314 var. So, therefore, this becomes equal to in the complex term a volt ampere perspective. So, Q is here positive. On the next part of the complex power for the current source 3 with an angle of minus 60 degree ampere current source, the voltage across is as already mentioned V 2 minus V 1. So, we will find the V 2 minus V 1 and we multiply the corresponding I conjugate. So, this gives us the corresponding V 2 minus V 1 substituting V 2 and V 1. So, we got the corresponding and then current conjugates plus 60 degree now. So, we got it to be 10.157 minus J 14.134 volt ampere. This is watt part, this is var part, var part. So, this var is having a negative value, Q is having a negative value here. So, we got the corresponding complex power associated with voltage source and the current source. Now, in addition to that, because we have the next part of the finding of the reactance part. So, you can see here the Q by 1 the reactive power, the resistance does not take any reactive power, they only consume the real power. So, the Q reactive power consumed or associated or delivered is nothing but associated the 1 farad capacitor and 2 Henry inductor. So, with 1 farad capacitor this becomes equals to minus x c nothing but b square omega c. So, that becomes equals to the corresponding thing happens to be this becomes equals to minus j 7.18 var b square omega c. So, now the corresponding Q by the 2 Henry 1 that becomes equals to the b square by j x c. So, that becomes equals to j 5.18 var and this we got the corresponding value to be in terms of the corresponding Q contributed by the capacitor, Q contributed by the as well with the inductor. The next question is about to find the corresponding reactance as already discussed, which will be connected across here at this terminal. So, this reactance value what will be there, so that the corresponding Q contributed by the, so that the reactive power supplied and reacted by the voltage source becomes 0, Q associated with the voltage source becomes 0. So, as already mentioned in this circuit the generation Q var is by the two sources. So, from the earlier calculations we find out that the corresponding power calculations, if you see here, then the current source have a minus Q and the voltage source having a plus Q of 12.31, this is having a current source having a minus 14.314. So, we say that minus 41.314 by the current source and the voltage source having a J 12.314. So, if we add this one, so that becomes equals to minus J 2 var, J 2 var. On the load side we are talking about reactive power on the load side the Q var only the inductor and the capacitor. So, we have calculated earlier. So, the inductor happens to be this part, inductor part, and the capacitor happens to be this. So, if you see here 5.18 plus and minus J 7.18. So, this become also minus 2 J minus J 2 var minus J 2 var. So, we say that the generation part and the load part they do match in terms of the reactive power. So, also the real power also. So, our business here is only to handle reactive power, because we like to find out the corresponding x value. And when we add the corresponding x here, j of x, what is the situation? So, you see here, because we like to make the corresponding generations the voltage part to be 0 without changing any change in the contribution of the reactive contribution of the inductor the current source part, because I told you that the voltage here remains fixed. So, even if you connect the J x, this side circuit does not change, no current, no voltage will change. So, therefore, if you see this, then the corresponding current reactive power contribution minus J 14.314 remains, but now the corresponding contribution of the voltage source reactive power that becomes equals to 0. So, that 0 how it will happen? It has earlier 12.314 J plus value. So, you have to subtract minus J 12.314. So, therefore, if you are subtracting minus J 314, we need to subtract in the corresponding contribution from the Q by the load also. So, Q by the load from the first one the reactor part, reactance part, inductor part is already J 5.18 this part, and contributed by the capacitor is minus J 7.18. So, now the additional one minus J 12.314 will come from this J of x, which we are talking about the additional one. Now, how does it come? You see here that I told that P plus J Q equals to V square by Z conjugate. This formula we know from our earlier discussion. So, from this formula we are talking about only J x, only J Q, because it is associated with only x. So, therefore, V square by minus J x, because minus J x means Z conjugate, if you are considering it to be J x. So, that becomes equals to minus J 12.314. So, therefore, the minus J x becomes equals to plus J 1.3, and the x happens to be equals to minus 1.3 ohm, or directly from here also you can say that if this becomes equals to J x. So, the corresponding x becomes equals to if this is given by the J x. So, this becomes corresponding Q. So, this results in the corresponding equating the V square by J x term, we got the corresponding x happens to be minus 1.3 ohm. So, this is nothing but a capacitor. This is nothing but a capacitor. So, you need to connect a capacitor whose reactance happens to be minus 1.3 ohm. So, then in that case this corresponding source, voltage source, reactive power becomes 0 in this circuit. So, that is the conclusion from this circuit analysis aspect. So, we say here that the concept here is that load and generation they do balance the power P and as well as Q part. The next example is on the circuit like this, and if you see this circuit, it is a voltage source of 250 volt, and we have a reactance J 20 and minus J 10 in series like this, but not series, it is at A and B they are connected shorted. So, 15 ohm and 10 ohm are in series, but the midpoint of these series connections of upper branch and lower branch are connected short circuited, and the question asks is that with a downward current I, find the value of the phasor I in the circuit. If you remember, such a circuit analysis similar to that only with resistance we discuss in DC circuit also. So, there we use the concept of Thevenin's equivalent at across terminal A and B, and using that Thevenin's equivalent we solve the circuit. Here also what we will do is that similar to that we have the circuit like this. Let us say this is J of 20. So, in series with this A terminal, in series will be minus J 10 ohm, and then we have in parallel we have 15 ohm, this is B, and we have 10 ohm resistance. So, the lower branch having 15 ohm and 10 ohm resistance, upper branch having 20 ohm J 20 ohm and minus J 10 ohm reactances. Now, this is connected to a voltage source, this is connected to a voltage source as shown here 250 volt 0 degree. What do you say that across AB if you find the corresponding Thevenin's equivalent, then what will do that finally the corresponding Thevenin's equivalent across AB will be look like this VTH and then ZTH, and this will be your AB terminal, AB terminal. So, what do you do that we do not have an impedance or any source or so between A and B. So, we will sort this and we will find the corresponding current to this. So, this current I becomes equals to VTH upon ZTH. So, that way you can solve the corresponding circuit problem. So, therefore, there are two parts here, we will find the corresponding VTH and ZTH by opening the corresponding short circuited path AB. So, we will go one by one for this case. So, first we will find the VTH. So, for VTH we open this, and to find the VTH what we do here that we will find the VA phasor and find the VB phasor, and then we will find the corresponding VA minus VB, that equals to VAB, and VAB is nothing but your VTH. So, now how will find out the corresponding VA? VA if you see this, because the voltage across this branch, let us say this branch is nothing but the current will flow through this one, and this across this is nothing but 250 volt. So, what is the corresponding voltage from this side? If you see the voltage across VA is nothing but the corresponding current in this branch, current will be 250 upon the corresponding impedance. So, 250 current will be 250 divided by J20 minus J10 into the corresponding minus J10 will nothing but corresponding VA. Similarly, VB will be equals to 250 divided by 15 plus 10 into the 10 will be nothing but VB. So, the VA becomes equals to, as I said, minus J10 into the corresponding current 250 upon J20 minus J10. This gives us the corresponding VA to be minus 250 with 0 degree, and VB equals to, similar to that, current is 250 upon 15 plus 10 into 10, this 10. So, that becomes equals to 100 with 0 degree with reference to this point. Now, therefore, VAB becomes equals to VA minus VB. So, if you substitute this, we got it to be minus 350 with 0 degree. Minus 350 means B is having a higher voltage than A, if we see the negative sign from the voltage. So, this is nothing but your VAB, this is nothing but your VAB. Now, we will go for the VAB you obtained. So, now you go for the ZTH Thevenin's equivalent. So, in Thevenin's equivalent, what you see is that this voltage source will be shorted, this voltage source will be shorted. Let us say we define this as C and this becomes D. So, the circuit becomes like this at A and B, these are A and B, this will not be there for this ZTH. So, A and B term, and then we have J20 between A and C J20, between A and D minus J10, and between B and C we have 15, we have between B and the corresponding D is 10. So, these are connection. So, we will find the corresponding impedance between A and B. So, these two are in parallel and these two are in parallel and they are in series. So, ZTH becomes equals to J20 and minus J10 in parallel and 15 and 10 in parallel, and they are connected in series. So, this gives us the corresponding ZTH value to be equals to 20.88 with minus 73 degree. So, equivalent impedance comes out to be a capacitive circuit. So, this is about this Thevenin's impedance. So, the Thevenin's equivalent becomes like this, minus 350 with 0 degree volt with positive side having A terminal, and then because we have taken VAB, VA minus VB, and then we have the Z Thevenin's to be equals to 20.88. So, this gives us the corresponding VAB to be equals to this and ZTH is this. So, the corresponding I can be computed, I becomes equals to minus 16.76 73 degree ampere. So, this is from A to B. If we consider this minus sign, otherwise from B to A it will be 16.76 with an angle of 73 degree. So, that way also you can express the corresponding current, because in the question circuit the current direction is shown to be downward. So, we are finding the downward current. So, in phasor terms it happens to be minus 16.76 with angle of 73 degree ampere. So, this is what we can solve the circuit for this case. Now, we have another problem in a series RLC circuit, descriptive problem rather, series RLC circuit, series R, L, L and C. L is varied, so it is variable, L is a variable, this C, to produce resonance keeping the supply frequency and C fixed, this C is fixed. So, let us say this is supply frequency, voltage supply, frequency is fixed. The circuit contains R to be 100 ohm, capacitive reactance XC to be equals to 200 ohm, so minus JXC this is, and F is 50 hertz, this is 50 hertz, and the supply is 1000 volt. Find the voltage drop across L at resonance, find the voltage drop across L at resonance and also when the drop across L is at maximum. So, we will go one by one. So, at resonance it means that XL value matches with XC and so also the VL equals to BC magnitude wise. So, that we know. So, therefore, the corresponding current to this path becomes equals to V divided by R, current to this path becomes V divided by R. So, I into VL becomes equals to I into XL, but XL equals to XC. So, VL equals to VC. So, we can find the value of the VL, VC and that will be nothing but the corresponding VL value. So, that way we go. So, then at resonance XL equals to XC, so Z becomes equals to R. So, IS becomes equals to Vs by R equals to 1000 divided by 100, that gives us 10 ampere current in the circuits, 10 ampere current. So, 10 into the corresponding XC, that gives us 200 volt because this is 200 ohm. So, 2000 volt. So, 2000 volt will be there across XL or XC, which is higher than 2 times that of the input voltage. So, that is the magnification factor of 2. In the second part, we have this, find the drop across L is a maximum when the corresponding the drop across L becomes maximum. So, find the value of L the VL rather when the VL becomes maximum by varying will vary the L such that the voltage across L becomes maximum. Note at resonance current is maximum, VL and VC they do cancel, but that does not guarantee that VL will be maximum there. So, that maximum condition we will find from the simple differentiation principle and so. So, what you say that the VL voltage across VL at any value of L, that equals to Vs upon the impedance, impedance is nothing but R plus J XL minus XC, J XL minus XC, these are Z, magnitude of Z is R square plus omega L minus 1 by omega C square. So, that we know. So, this is nothing but the corresponding VL magnitude and Vs source voltage upon this impedance magnitude into the omega L, that is XL. So, XL into the corresponding current is nothing but the corresponding VL. So, we go by this, then the drop across L is maximum when dVL by dL equals to 0. We go on varying the L. So, with respect to L, the inductor value dVL by dL equals to 0, maximum value. So, this maximum value condition if you put. So, then differentiation of this dVL with respect to this L, if we go by this and part by part, then we equate this to be 0, then we got this L to be equals to C R square plus 1 by omega square C square, and we multiply with this L to omega because it is 50 hertz fixed value, then the corresponding XL value happens to be equals to 1 by XC, 1 by XC, C is given to fixed, 1 by XC is rather 200 R square plus XC square. So, this is the corresponding condition for XL when it becomes maximum. So, let us go by that. So, when we see that the XL equals to 1 by XC R square plus XC square. So, if we substitute this value, we got it to be 250 ohm, R is 100, XC is 200. So, if we substitute, then we got the corresponding XL value where VL should be maximum, that equals to 250 ohm. So, we got the XL value to be 250 ohm. Now, at 250 ohm the corresponding I current we can find out. So, I equals to Vs upon R plus J XL minus XC. So, we substitute the XL to be 250, XC to be 200 and R to be 100 and V is having 1000 volt. So, we got the corresponding current at that time to be equals to 8.944 with an angle of minus 26.565. So, the current shows that at this time the corresponding circuit is inductive and also true because XL is greater than XC, 250 minus 200. So, it is plus Jx. Now, the VL corresponding VL at that time for that current I into the corresponding VL that time, that becomes equals to with 250 multiplication we got the corresponding voltage to be 2236.07 volt, 2236 volt. So, this is higher than the earlier resonance case. The resonance case we got the corresponding value to be 2000 volt, if you remember in the earlier slide. So, this value VL happens to be higher now. So, this clearly shows that at resonance point the corresponding VL is not maximum, VL is maximum at a different point if you have a scope of varying the inductance value. The corresponding L at that time is nothing but XL divided by omega, and this becomes equals to 0.7962 Henry for this case. Now, here is a plot which shows about the corresponding VL versus the corresponding L. So, this is L, this is VL in voltage. Then this plot is a trend like this. So, with L increasing, then the maximum value comes out to be here, and this is nothing but 2236.07 volt, 2236.07 volt at this point. So, this is at the point corresponding point is 0.7962 Henry, and beyond that also the corresponding L value decreases, and so. So, that is the from the differentiation of dVL upon L we get this operating point at which the VL happens to be maximum in this case. So, this is what we solve the case when the VL becomes maximum. Before closing the AC circuits, I like to say something on more on the phasors. So, phasor is a very powerful technique in AC circuit analysis. We started with phasors, and in all perspective we analyze the corresponding AC circuit in terms of the phasors. So, phasor is in the frequency domain, we have seen from time domain to frequency domain, and that makes our analysis perspective pretty easy. Now, phasor is a complex quantity that represents both magnitude and angle. A sinusoidal quantity is represented by phasor, a vector rotating anticlockwise with the speed of omega. That is the representation. So, I equals to Im sin omega t, B equals to Bm sin omega t plus phi. So, you see the corresponding I and this rotating with a speed of omega both continuously, and then we say that we represent them in terms of Vm by root 2 the RMS value and Im by root 2, and angle between them is phi with the corresponding voltage leading the corresponding current by phi in this case. So, at this instance we take the corresponding these to be I equals to a reference phasor. If so, that with a 0 degree, then V becomes equals to with an angle of phi degree, and this is polar form. In rectangular form we can put in terms of the cos phi plus j sin phi into the corresponding Vm by root 2. So, these are the corresponding phasor impedance in terms of that, but the phasor analysis is only applied the corresponding frequency is constant, frequency remain constant 50 hertz frequency FR. So, corresponding omega with that speed it rotates. If the frequency goes on changing, then the corresponding things cannot be analyzed, because this is anticlockwise rotation with a constant speed of omega. That is one condition. It applies in manipulating two or more sinusoidals if they are having the same frequency. If the I and V or V1 and V2 at two voltages are having the same sinusoidal frequency, then only we can use the corresponding phasor for the analysis. We can study them simultaneously. Now, another thing we notice that the J operator used for the phasors, like this J operator, which happens to be a 90 degree anticlockwise rotations, J makes its anticlockwise rotation of 90 degree, another J gives you 180 degree, and so. So, those are the important things we talk about phasor. But the another important thing is that if the corresponding signals, there are two signals, let us say I 1 and I 2, and they are having two frequencies omega 1 and omega 2, f 1 and f 2 correspondingly. Can you analyze them simultaneously? No. Now, let us see the reason. Let us say in this case I 1 is I m 2 and omega 1 is greater than omega 2. First phasor is having a higher speed as compared to the second, sin omega 1 and this is sin omega 2. What happens in the phasor terms which you have already seen? So, let us say for one instant of time t equals to t 1, in the phasor diagram rotating vector. So, this is I 1 and this is I 2, I 1 having smaller magnitude than I 2, and they have an angle at that time is phi 1, but I 2 is rotating a speed of omega 2 and I 1 is rotating with a speed of omega 1. Second instant t equals to t 2, this is the phasor corresponding at this instant, t equals to t 2, next instant t 1 greater than t 2. So, I 2 takes a position here with omega 2 speed and I 1 takes a position here with omega 1 speed, because omega 1 is greater than omega 2. So, the advancement of I 1 will be more than as compared to I 2. So, this corresponding phi 2 becomes now, the phi 2 becomes greater than phi 1 now as compared to this. Third case T 3 greater than T 2. Now, T 1 I 1 takes a position here and this is the corresponding I 2 takes a position here, I 1 takes a position here, because the speed of I 1 is higher than the I 2. So, the corresponding phi 2 phi 3 again becomes equals greater than the phi 3 becomes again greater than phi 2 and phi 2 greater than become phi 1. So, the corresponding things what will happen, the rotation of this vector we call it phasor, they go on with a different speed and then therefore, what will happen, the angle between them will be not constant and therefore, the corresponding phasor comparison does not stay hold good. It will be continuously changing in terms of that and our phasor analysis will not be useful for in that perspective. So, therefore, essentially we say that phasors with same constant frequency, phasors with same value of frequency are meaningful, otherwise it becomes purposeless. So, this is about something on phasors we talk about. So, in overall here in this lecture we talk about more complex problem on AC, and this with this we finish the corresponding AC circuits aspect, dealing with from the starting from the concept of impedance, reactance, impedance, complex power, reactive power, power factor improvement, theorem perspective application, nodal voltage, loop current, and so. Thank you.